Hello. Can you hear me? I can't hear you. Oh,
Hello.
oh, hi.
Hi. Are you able to see my screen?
Yes.
Okay, excellent. So today we were going to do this long answer problem 3 of 4 and the exercise 10.47.
Yeah.
Have you had a chance to look at either of them yet?
No, sorry.
Okay. So how about we start with this two pucks problem?
All right.
Module 6. And long answer problem, right? Okay. So do you want to take a look at it first, or how do you want to do this? Do you want to take a look?
Yeah, I'll take a quick look. Bug uniform disk of mass m and radius r traveling at a speed v on a frictionless tricks aside. All right. All right, I see.
Okay. So the first question is asking what the angular momentum of the system is at point A. I mean, sorry, at around the point P before the collision.
Uh, there won't be any because it's oh wait, yeah, because there's no angular velocity of the pucks. It's just nothing at before it collides.
Okay, but do you know this formula? Angular momentum equals R cross linear momentum.
Right.
You know that formula?
Yeah.
I guess they taught that this week.
Yeah.
Okay, so um, so um, so I'll draw here. We have this thing moving with velocity v, and that they told us the mass of it, right? A puck is a uniform disk of mass m and radius r traveling at speed v. So there's a radius r and a mass m. And then we have this point P. So there's some distance between this object and P. So it has linear momentum P, and it has some angular momentum around this point P, right?
Yeah.
Yeah. So How do you think we would go about this?
Well, I'm still thinking there's no angular momentum because it says before the collision, right?
Yeah. But if we were to just calculate r cross p, in fact, lowercase r is the radius of this. So I'm going to use capital R for the position there, because lowercase r was already given as the radius, not the displacement away from the pivot point.
All right.
So the momentum vector, so I'll use different color now. The momentum vector is like this, right? That's
Yeah.
P. And then what about the capital R vector?
Well, when it collides,
Before it collides.
yeah, right before, would it just be the radius or would it be like 2r? I think it is just the radius.
Yeah, so before the collision. Okay, so so the capital R vector, that's typically going from the pivot point to from the pivot point to the object.
Right.
Now, before the collision, okay, so when they collide, we will have so I can draw another version of this where I just have them collided. Oops.
So about point P, that means, yeah.
So that's P. That's a radius of R. And so
And the angular momentum would be, where would it be exactly?
we still have linear momentum of P. Worry, I'm drawing this a little bit too close. So, okay. So this is like immediately before the collision in the second diagram. So I have my P vector like that. What about my capital R vector?
So it would be from, just thinking where it's from the pivot point to where again?
To the object, to the center of the object.
So the center of the object, would it be? Oh yeah, yeah, so it is just R.
Yeah. Okay. So now, how about the cross product? How are we going to evaluate this cross product?
So that would be the magnitude of both times each other times sine of theta.
Excellent. And they didn't use theta for anything else, so I can call theta whatever I want. And now the angle between R and P, what is that equal to?
90 degrees.
90 degrees, okay. And then sine of 90 is what?
It's just 1.
Yeah. Okay, so in the end, we have, and what's the magnitude of the R vector?
Lowercase r.
Okay, and then what's the magnitude of the P vector?
Just P.
Well,
Or
it says express your answers in terms of M, R, and or V.
oh, so it would just be instead of just P, it's just M times V. So RMV.
Yeah, so even though nothing is rotating, around this pivot point P, if it's traveling with a linear momentum P, and it's going to the right with a linear momentum P, right? Then it does have an angular momentum of RMV.
And yeah,
because around that pivot point P, there is a vector tangential to it and that vector p, which is tangential to it, happens to have a magnitude of mv, and it's a distance r away from the pivot point p. So there's angular momentum even though nothing's rotating or rolling.
I understand.
That makes sense. There's angular momentum by virtue of the fact that there's linear momentum a distance r away from the pivot point.
Okay, so yeah, it kind of makes sense.
Okay,
It's,
now part B.
I guess I just shouldn't assume there's no angular things when things aren't spinning.
Yeah, there's no angular velocity, but there is angular momentum.
Right.
Yeah. So, yeah, I mean, you might even be able to say that there's angular velocity somehow, but the main point is that you know how to calculate the angular momentum in this type of case using r cross p.
Oh. Okay, so parallel axis theorem.
Yeah, parallel axis theorem to determine the moment of inertia of the two-puck object about its center of mass.
Well, to use parallel axis theorem, you would need the center plus the rotational at a certain point.
Yeah.
And that. Wait, wouldn't the center of mass be where point P is?
Yeah, so when the two pucks collide, like in this diagram, for example, is that what you mean? Like you're talking about this diagram?
Yeah.
Yeah, the center of mass is at P. So you want to, do you know this? Do you know the moment of inertia of two disks around a point P?
Well, it would just be a inertia would be two times the mass times r squared because both pucks are identical.
Okay. What's okay? I'll just draw this again. So we have two pucks. Those don't look very identical. So we have two pucks. There's a center of mass here. And do you know the moment of inertia for a two puck system?
Oh, is it a certain value?
Well, it is, but we don't know it, right? We know for a disk it's half mr squared, but we don't know what it
Oh,
is for two disks, right?
right. I was assuming it was just one mr squared because I'm used to just points, not actual objects. So
Yeah, so for a disk, it's not going to be the same as what it is for just
a disk is half mr squared.
yeah. So for each disk, you have half mr squared. So this is puck one, this is puck two. So
if there's two of them, it would just be mr squared if you add them together.
okay, hold on. So moment of inertia of puck one is equal to the moment of inertia of puck one around the center of mass plus the parallel axis theorem. Right? What am I going to get from the parallel axis theorem?
Oh, well, well, I'm just a bit confused because I'm confused on why you're using parallel axis theorem here exactly.
Okay, so let's just let's just say there's one disk. What is the moment of inertia of that disk around the point P?
Well, it would be the mass of the puck times the distance from the center squared.
The mass of the puck times the distance from the center squared.
Yeah.
Um, what about the moment of inertia of the center of mass?
All right.
So do you know the moment of inertia about the center of mass of a disk?
Oh, I see. Okay, so for the first puck, it would be a. Okay, so it's two things. It's the inertia in its center and the inertia at the pivot point or the center of mass.
Yeah, so the moment of inertia of puck one around its own center of mass, what is that?
It's center of its mass. So that would be and you said it's half, right?
There is a half in the formula for it.
So it would be half of half of m times 2r squared,
Um,
or
just half mr squared.
yeah, I was thinking about the pipes and how you use its length.
Yeah, and
Sorry.
for the moment of inertia of a disk around its center of mass, it's just half mr squared.
All right.
Okay, now we're using the parallel axis theorem to figure out what the moment of inertia of puck one is around pivot point P.
Well, it would be the mass times the distance from the point of inertia squared.
So how much is that?
It's just r.
Okay. Okay, and now what about for puck two?
For puck
The
two,
moment of inertia of puck two around the pivot point P.
would it just be identical, or would
Yeah.
you need to? I guess direction isn't. Yeah, it's momentum. No direction is required. Or wait, is it? Oh, it is. Sorry. So not for inertia, right?
What's not for inertia?
Direction, because if it's required, then I the inertia of the second point would be the negative of the first because it's. But yeah, I'm confusing myself.
Well, moment of inertia is a scalar. There's no direction associated with it.
Yeah.
So, okay, so we just end up with the same thing, right? Half mr squared plus mr squared. Now the moment of inertia of the whole thing, I around pivot point P equals moment of inertia of the first puck around pivot point P plus moment of inertia of the second puck around pivot point P. So this would be equal to 2 times half mr squared plus mr squared, which equals 3mr squared.
All right.
Okay.
Yeah. I'm gonna write this all down. Just
Yeah,
should
I'll
be
be
writing
giving you
with you.
this too.
All right. So yeah. This. All right. Part C.
Yeah, so part C, using conservation of total angular momentum, determine the angular velocity omega.
Yeah. So total angular momentum. Oh, does that mean L is equal to L? Is that what they're trying to say?
Well, L equals L isn't a very meaningful
Oh,
equation.
sorry. L initial equals L final, or
Yeah, L initial equals L final. So L initial we already calculated.
yeah,
What was L initial equal to?
3 mr squared.
That
Or
was moment of inertia.
all right. We have a RMV.
RMV. Okay, so RMV is the initial angular momentum, and what about the final angle?
Well, to do that, we could convert L into I times omega.
Exactly. Very good. Very good. And now we know I, right?
Yeah, we just calculated. That's 3 mr squared.
Okay, so it's easy to get omega now. Oops, what did I just do? I clicked on the wrong thing. I wanted to just click on red. Okay.
All right, they got an answer.
Okay, so what did you get?
3v over r. Wait, oh, oh, yeah, sorry, v over 3r.
Yeah, why did you get 3v over r?
I don't know exactly. I just should have thought it through a bit more.
Okay, so now part D, we're going to use conservation of linear momentum.
All right. So that's after. So we could do L final is equal to the cross product of r times p.
So
Oh,
that's true. The final, well, no, L final is equal to I omega, right?
oh wait, no, we could just do pi equals pf.
Yeah, because it's conservation of linear momentum, right?
Yep.
Pi equals Pf. And what's Pi?
Initial it's just mv.
Okay, and Pf?
It's also well, in this case it would be 2m capital V because both masses are in effect now.
Exactly. And then it asks you for V, right? So capital V.
Yes,
So
so V is equal to V over 2. So half of the initial speed.
exactly. Yeah. So oops, what's happening here? Exit that. Okay. Okay. Okay, so part E, the last one. All right, so E, we have, what is the change in kinetic energy of the system? Express your answer as a numerical fraction of the original kinetic energy of the system. So we want the change in kinetic energy as a fraction of the original kinetic energy. We want delta K equals some fraction of the initial kinetic energy. Does that make sense?
Yeah.
So
Wait.
what's P and Q?
Wait, actually, I don't fully understand P over Q.
So we want to write delta K as a fraction of the initial kinetic energy.
Okay.
So maybe 3/5 of the original kinetic energy. Then P would be 3 and Q would be 5.
All right.
So how would we start this?
Well, we could change. Uh, I'm a bit confused on how to start with this one.
How do you usually write the change in kinetic energy?
The well, it would be final minus initial, right?
Yeah.
Yeah.
And then you know the final kinetic energy?
The final would be well, we have V and we have M. So yeah, we do know.
Okay, so what does it equal?
KF is equal to half of mv squared, but m is 2m, and the velocity is v over 2.
Okay, and that's the translational kinetic energy.
Oh, and then you add the rotational.
What's the rotational?
It would be inertia plus it's yeah, it's equal to half of inertia omega squared.
Okay. And the initial kinetic energy?
The initial kinetic. Oh wait. Oh. Wait a second. The initial would be half of mv squared.
Okay, so how are we going to do this now? We want to write delta K as a fraction of Ki. And what's Ki equal to?
Ki is equal to Ki is equal to. Wait, what exactly do you mean?
Well, Ki is equal to half mv squared. So we want to write delta K as a fraction of that. How are we going to do that?
Uh, well then, half of mv. Well, half of mv. I don't really know. Wait, could you say? Sorry, I'm getting confused. Can you say that again?
Okay, we're gonna have to write delta K. So this whole thing is delta K.
Yeah.
We're gonna have to write that in the form P over Q times Ki.
Yeah.
So right now we have something minus Ki, but we want to write it as Ki times something.
Right.
So we
Well,
basically want to we
well,
basically want to factor out a Ki, right?
yeah. So, change half of mv squared back to ki, or
Yeah, yeah.
yeah, since yeah, ki. I don't really know what to do next.
Okay, so is there a way to write this capital V and omega and all of this stuff in terms of Ki?
Right. Well, in terms of ki, uh, well, for omega, there's only a final omega, no initial. But for linear speed, yes, we could change capital V into small v over 2.
Okay, so we just have m times v over 2 squared.
Yeah.
And what about for the other part?
For omega, I mean, omega could equal v over 3r, but I don't know what to. And
Okay, so I equals what?
uh, I initial inertia, we have 3mr squared.
Mm-hmm. So 3mr squared. And what about omega?
We have v over 3r.
V over 3r. Yeah, we calculated that. Yeah, we calculated that in the last step. V over 3r squared
Yeah,
minus.
it's all gonna work
Yeah.
out.
Pardon me?
It's all gonna work out.
Okay, so how's it going to work out? What did you do? You just expanded everything?
Yeah, because the r's cancel out. Then we change the capital V into little v in omega, and then there would all be multiples of m in lowercase v. And as we know, ki is equal to half of small m small v squared.
Okay, so we have 9r squared, and then those cancel out. So we're going to have, so this cancels out that. Okay, so, all right, we have now 1/2 times ki. That's what the first term is, right?
Yeah,
Plus 3 over 9 times ki, right?
yeah.
This is mv squared over 2 times 3 over 9. Okay, minus ki. So now we can factor out a ki, right?
Yeah.
Okay, so we have, this is 8, well, over 18. This is going to be 9 over 18. 9 over 18 plus 6 over 18
So
minus
15.
18 over 18, right?
So 15 minus 18, negative 3 over 18.
Yeah, and then that can be simplified even more, right?
Yeah, 1/3, -1/3.
Negative 1/3 ki. Excellent. So your p is equal to -1 and your q is equal to 3.
All right.
Perfect. Does that all make sense to you?
Yeah. Mhm.
Okay. So everything in this question makes sense?
Yep.
Okay. Should we move on to the that exercise 10.24?
Yeah.
Oh, sorry, 10.47?
Sure.
Okay.
All right.
Okay, so this is
Okay. So, uh, part A. Can you hear me?
yeah, I can hear you. Yeah. The large wooden turntable, that's the question you're looking at? The large wooden turntable in the shape of a flat uniform disc?
Yeah.
Okay. I can help draw it for you. Okay, so it's a radius of 2 meters, right?
Mhm.
Total mass 1.20 times 10 to the 2 kilograms. Okay. Initially rotating at 3.30 radians per second. About a vertical axis through the center. Okay. Suddenly, a 65 kilogram parachutist makes a soft landing on the turntable at a point near the outer edge. So this is what it initially looks like. And then at the end, you have some parachutist landing, and that person weighs 65 kilograms.
Yep.
landing at the edge, basically, right?
Mhm.
Okay, so find the angular speed of the turntable after the landing of the parachutist. Assume that the parachutist doesn't have any radius or size.
All right. All right, so to start, hmm, don't really. Mm. Could you help me start, please?
Okay, so this is the same type of typical question where you have something rotating. It has a certain moment of inertia and it starts rotating. Then something about the geometry changes. What happens to the system when this parachuter lands? How does that change the system?
Well, the parachutist would. What I must be having a brain fart or something. Could you please at least start the question?
Okay, so this starts the same way as it did when we had a fan, where the fan blades were spinning around, and then there was this insect that ended up at the end of one of the fan blades. That changes something about the system. Do you remember what it changes?
Yeah. It changes its linear speed, right?
Um, okay, the speed will change, but why is that?
It would change because it has a larger radius. Well, I mean distance away from the center.
Okay, and what has a larger distance away from the center?
The skydiver or the bug in that other case.
Okay, so yeah, so I have this disk that's rotating. The disk is rotating in a certain way, and then suddenly something lands on that disk. How does that intrinsically change? What property of the system changes when something lands on it?
Uh, oh, the inertia, right?
Moment of inertia.
Yes, yes, moment of inertia.
Yeah. So at the beginning, the moment of inertia was a certain amount, and now you have to add mr squared to it, right?
Mhm.
And then if the moment of inertia changes, then what else changes?
Uh, well, inertia is equal to mass times mr squared. Not Yeah, mass times r squared.
Yeah,
Or
so inertia is equal to that. And if mr squared changes, so inertia changes, moment of inertia changes.
yeah, so if moment of inertia changes, uh, okay. Sorry, I must be having a bit of a rough day today.
Yeah, okay. So what about when a figure skater is spinning around and then the figure skater's radius changes? What happens?
If the radius changes, then the inertia changes, right?
Yeah, because the figure skater pulls their arms into their chest and now their radius is smaller. What does that happen? What happens to their spinning?
Uh, their spinning their spinning increases.
Yeah, and do you know why that is?
That's because their their radius decreases.
Yeah, and okay, so the radius decreases, and so the spinning increases. Do you know the underlying principle for how to quantify that?
Uh, quantifying principles. So I'm trying to remember. Okay, so when the skater closes their arms,
Yeah,
the their radius, like how much like space they take up, decreases.
yeah.
And when that happens, that means the I guess that means their angular speed increases because they're rotating faster.
Okay. How much does it increase by?
Well, I can't seem to remember what angular speed is equal to. Uh, it would be equal to angular displacement over time.
Okay. Do you remember that I initial times omega initial is equal to I final omega final? So
Oh, right, right.
I omega is conserved, right?
How did I forget about? Yeah, should have used conservation of angular momentum again.
Always when the geometry of a spinning object changes.
Got
So
it.
you have a spinning fan blade, and there's some insect that lands on the end of the fan blade. How does that insect change the spinning? Well, it changes the moment of inertia. And if you increase the moment of inertia, then you have to decrease your angular velocity. If you decrease your moment of inertia, then you have to increase your angular velocity because I omega has to stay conserved. So if a ballerina is spinning around and their arms come closer to their chest, then their moment of inertia changes because their moment of inertia gets smaller and therefore their spinning has to go faster.
Yeah. All right. So now that we have this, we have I initial, omega initial, equal to I final, omega final. So we have initial omega, and yeah, the question's asking for final, right?
Yeah.
Yes. So um, I guess the only thing we need to do is calculate the inertia, like initial and final inertia, moment of inertia, I mean. So to start, well, the inertia in this case, would it just be of the skydiver?
The initial moment of inertia. Well, what's
I mean, sorry, I didn't mean skydiver. I meant the mass on the turntable.
yeah? So the moment of inertia of the turntable is the initial moment of inertia.
Yeah. Okay, so the initial inertia. Uh, well then, it would be it would be, well, I'm just constantly thinking of it. Do we use parallel axis theorem in this case, or
If you want to, but at the beginning we don't even have a parachuter. We just have the disc. We just have a rotating disc.
right? Well then, I guess there's no inertia at the start.
Well, how can there
Right.
be no moment of inertia? There's a disc.
Oh, one. Well, okay. So for inertia, we just calculate the inertia at the center, or
Okay, so anytime you're doing a moment of inertia, you have to choose a pivot or an axis.
yeah. Well, that makes sense. That's at the center of the turntable.
Yeah. Well, yeah, the rotation is around the center, right?
Yeah.
The rotation, the axis of rotation is a vertical axis going through the center.
Yeah. So that would, okay, so we just calculate inertia at the center, right? Or
Yeah, yeah. The moment of inertia will be calculated about the axis of rotation, and in this case, the axis of rotation is a vertical line going through the center.
yeah. Okay, so we have, okay, so in a disk, it's half, right?
Yeah,
So we have half. Uh, let's keep the mass just m at the moment.
very good.
Uh, and then r squared. Yeah, and we could also do r later. And then oh, initial omega, which we could still keep as that. And then as for the final inertia, we would have both the inertia at the center and the inertia of the parachutist.
Yeah.
So would it just be the inertia of the parachutist plus the inertia at the center for IF?
So it's going to be the moment of inertia of the disc plus the moment of inertia of the parachuter, right?
Yeah. So would the disc would remain the same, right? Or would it add the mass of the parachutist?
So we're going to do the moment of inertia of the disc plus the moment of inertia of the parachutist.
Right. No, I'm sorry. What I mean is for the inertia of uh yeah, I was thinking for the inertia of the disk, um ever since it's like a 2D, like it's an object and the parachutist lands on the disc,
Yeah.
I'm thinking would you add the mass of the parachutist for the inertia of the disc?
Okay, let me write this out. Like I disk around the center of the mass plus I parachuter.
So it's just the mass of the disc for the inertia of the disc. I know it's a weird thing to say, but like I was just again, I was thinking that the parachutist lands on the disc.
The parachuter does land on the disc, but it's just like when we did the fan blade. The fan blade is spinning around, and there's some
Yeah.
insect that is on. So the moment of inertia after the insect lands on the fan blade is basically the moment of inertia of the fan blade plus mr squared, where m is the mass of the insect and r is the distance away from the pivot point.
All right. So if that's the case, then the inertia of the disc would remain the same.
Yeah.
It would be half mr squared. And then of the parachute, it would just be m, so capital M.
Okay.
Or yeah, M2 is also good.
Yeah.
M, and then it's also R because it's that far away from the center,
Exactly.
and then squared,
Yes.
and then times final angular
Okay,
velocity.
and I'm going to call it omega 2 because that's what they call it in this question when they're asking
Right.
for the answer. Okay, so now we can solve for omega 2.
Yeah, so you just divide the final inertia we just got.
Yeah, but before we do that, let's first get rid of these fractions, because if we take half mr squared and divide it by half mr squared plus m2r squared, we're going to have two fractions, a fraction in the numerator and a fraction in the denominator.
Right.
And then we're going to have 4 lines worth of writing to do, and it's just going to take up more and more space, and then you might run out of room or something. So let's multiply everything by 2.
Yeah.
So we'll get mr squared omega equals mr squared plus 2m2r squared omega 2. And now, instead of fractions, we're just dealing with one line. So now we can get omega 2 equals mr squared omega all over mr squared plus 2m2 r squared. Oh, and these r squareds, they all cancel out, don't they? Isn't that nice?
Right. Over. Just a second, I'm writing it all down. R.
Okay, so, oh, why is that happening? Undo. Okay. So that's it for part A.
Yeah, we could just sub everything in now.
Oh yeah, okay. We can also sub everything in because they want a numerical answer in the end, right?
Yes. So we do that. Initial angular velocity is where is it? 3.3 radians a second.
That's right.
The mass of the turntable is 1.2 times 10 to the 2, or 120. Then you divide by all right, I got around 0.49.
For radians per second?
Or 0.493. That's what I got.
Radians per second, right?
Yes.
So the moment of inertia increased, and therefore the angular speed has to decrease. So it makes logical sense. Did you want me to type it in my calculator too?
Yeah, go ahead.
Okay. All right. So mass 1 so it's 120 kilograms, 120 times 3.3 divided by 120 plus 2 times 65. I seem to be getting 1.58. I seem to be getting 1.58.
I'll try again. Perhaps it's a calculator.
120 times 3.3 divided by 120 plus 2 times 65.
Still getting 0.49.
Hmm.
Two.
Let's see.
Oh, wait. Mass times angular. Oh,
Well, the formula I have here is mass times angular velocity.
I did plus angular velocity. I don't know why.
You can't add something in kilograms to something in radians per second and get away with it.
Right.
You have to have the same units if you're going to add them.
Okay, that makes sense. Let me do it again. Yeah, 1.58. Excellent. Okay, part B. Initial kinetic energy. So, well, I was gonna say it would just be 0, but I remember in the last question, I assumed angular momentum was initially 0, and then I was wrong, so I don't really know. Like, I think it's 0, but it might not be.
So you have a flat uniform disk spinning at 3.3 radians per second, and you're saying it has no energy?
No connect. Oh, what am I thinking? I was just thinking about linear kinetic energy, not total.
Tangential kinetic energy.
Like, yeah, linear in linear terms, yeah, it's 0, but in it's just rotational then.
Yeah.
Okay. So it would be half of inertia times yeah, it's half of inertia times omega squared. So half of moment of inertia, omega squared. Okay. So inertia, we calculated inertia because it's just half of mr squared. So we have of half of mr squared. And then the initial angular velocity is also given at 3.3, but we could leave it the way it is at the moment.
Mhm. And then how about the units? It said express your answer with the appropriate units.
Okay, so what we have here is we have mass, we have kilograms, R is meters, meters squared, and then omega is radians per second, and that's squared. Yeah.
That's just equal to joules. Radians are just measuring an angle. So I think it's okay to just say the kinetic energy is in joules.
Well,
Kilogram
is what-
meter squared per second squared.
well, joules is what energy is. So
Yeah. But we have radians squared here, but I'm telling you, you don't have to worry too much about that.
okay. And it also wants me to actually calculate it, so I'll do that now.
Okay.
So 3.3 squared multiplied by 2 squared multiplied by 120 divided by 4. I got 1,310.
Okay, you want me to calculate it too?
Yep.
Okay. So the mass of the turntable was 120. So 120 times 2 meters squared, which will be 4, times 3.3 squared, all divided by 4. So it's 1,306.8.
Yep.
So 1.31 times 10 to the 3 joules.
Good.
Okay.
All right, part C, final kinetic energy. So, what we could do, well, in this case, there would be both linear and angular. Wait, or would it just be angular still? Because the parachutist isn't moving, like he's only moving because of the turntable when he lands.
Yeah.
So I guess it would also just be half of at moment of inertia omega squared.
Okay. And we just know that the moment of inertia has changed, right?
Yeah.
What was our moment of inertia? The new moment of inertia, we calculated that at some
Yeah, we
point.
calculated that.
Half mr squared plus m2r squared.
Yeah. Yeah, it could. Yeah.
So that's the new moment of inertia.
And then the angular speed we calculated in
Yeah.
part A.
Yeah.
So we have m, and we have mass times the initial angular speed over mass times 2 times the parachutist mass. M plus 2 m2, and then square everything.
Let's see if we can simplify this. So we could factor out the r, right? So we have r squared over 2 times 1/2 m plus m2 times m omega over m plus 2 omega 2 squared. Not much more we can do, right?
Yeah, well, we could do more, but that would take a very long time because you have to put in the square and then multiply, and they'll be very large as well.
Yeah, we might as well just calculate it like this, right?
Yeah. So I will do that. 3.3 times 120. I got 627.
Okay, I'm just about done calculating. I got 627 as well.
All right.
627. What about the units?
Let's see here.
Meters
It
squared.
it should be joules again, but let's take a look. So we have meters squared times meter times kilograms times kilograms times radians per second divided by kilograms. And that would equal to all right, part D. Why are these kinetic energies not equal? So there's two options. In the changing period, what is on? Friction does positive or negative work. Um, so work. Let me think. Well, this shouldn't take too long, but let me think. Uh, work is force over displacement. Well, force times displacement. So would it be? I'm just confused what it means by positive or negative work. Hmm. Could you still hear me?
Yeah, yeah. So you want to decide whether it's positive work or negative work, right?
Yeah, that's the only two options.
Okay, so how would you do if it was an exam or a quiz and you were asked, you just calculated a bunch of kinetic energies.
Yeah.
So how is kinetic energy related to work?
Um. Oh, work kinetic energy theorem. Oh, work kinetic energy theorem. Well, so Friction is what friction removes some of the kinetic energy. So that means well, that would make the angular speed lower. It would slow it down. I don't know if I should use quirk kinetic energy theorem in thinking about this.
I think it's a good idea because they just made you calculate the initial and final kinetic energies. So
Right.
you
So,
just calculated the kinetic energies, and now they're asking you something about work.
wait a minute. Oh, this is easy. You just do final minus initial. So 627 minus 1,310. Then work would be a negative number.
So that's less than 0. So the work is doing, so there's negative work done, right?
Yeah.
Okay,
So it's the second option, right?
exactly. This is group work, right? So you're just explaining these answers to the class.
Yeah, to my group mates.
So you don't even have to submit these.
Nope.
Okay. Yeah, it seems you might need a bit more practice with this conservation of angular momentum stuff. Should we take a
Yeah.
look at another one of these long answer problems?
Well, I guess so because we still have 40 minutes and there's nothing left to do for tonight. So sure.
In module 6, long answer, we could do long answer. We did number 3, so we could do 2 or 1 or 4. Which
Two,
one do you
one.
want to do?
Let
Looks
me
like
take
there's an integral for, oh no, that's not an integral. That's just a big bracket.
let me see what the other questions are like.
Okay.
1, 2, and 4. All right, number 1, merry-go-round. That doesn't seem too bad. Number 2. Okay, and number 4 seems a bit familiar. So that one exam question we looked at.
Yeah, we did a merry-go-round in the exam already, right?
Oh, also in question 4, actually, wait, no, that's a bit different. Question 4 also involves angles. Well, I guess that's something to use these 40 minutes for. How about we do number 4?
Okay, I'm trying
Says
to
it.
figure out how to remove. I want to erase entire objects, click for one object, drag multiple objects.
So you click and hold.
Click and hold,
Yeah, like drag it, click and drag it, or
drag where?
just to the things you want to erase.
So I'm clicking this,
Hmm.
I click it and I hold. Looks like I can't really.
Yeah, I haven't used that software. I don't really know.
Yeah, this one looks so much nicer than the other one, but I just can't delete stuff.
You see how it highlights it when you
Yeah.
hover over it? Maybe that's what you need to do.
Yeah, it highlights.
It's like it's like it's like an error. It's like you're doing everything right. It's just not working at the moment.
It seems that might be the case, right? Yeah. Erase entire objects. What happens if I do this? Undo, undo, undo. That might be removing stuff from page 3. No, work is negative. That's still good. So page 2 is just a waste then. Page 2, yeah. I'll just make a new one. Okay. Page 4. All right. So, all right. Module 6.
Yeah, now we got a new page for this one. Right.
It's called Problem 27 Equilibrium.
Yep.
All right. Let's do this. Okay, a refrigerator of mass M, height H, and width W is at rest on an inclined ramp with coefficient of static friction mu s. Assume the center of gravity of the refrigerator is midway between its left and right sides. Okay, that would make sense. At a distance L above the bottom. The refrigerator's weight is distributed over its 4 feet. The solid black square is assumed to be negligibly small, but not necessarily evenly. So the weight is on the 4 feet, but not necessarily on each of the 4 feet. I mean, not necessarily the same on each foot. Draw a complete, properly labeled free body diagram for the refrigerator. Write Newton's second law for both translational and rotational equilibrium. Excellent. Okay. So we have this angle. We have the fridge. And it's got this width of W, height of H, and mass of capital M. And the center of gravity is L from the middle. Should actually do, so these are the 4 legs. And the length L is from its bottom. In that diagram, it looks like the length L is from the floor. Okay, well, they're saying that the 4 feet are assumed to be negligibly small. So drawing the L from the bottom of the fridge or from the ground doesn't make a difference. So that's the center of mass. Okay, looks like we have everything there. And now we've got to draw, this is a free body diagram, so we've got to draw what the forces are. So what are all the forces going to be?
Well, for this, let me just read the question again. So the static friction, but well, I don't think there's a force for static friction.
Why not?
I was gonna say because it's not moving, but I guess there is a force.
Why is it called static friction if there's no force?
Yeah, you're right. Okay, so there's static friction going up the ramp.
Okay.
So that's the first force.
Now, how big is the static friction?
Uh, well, I was about to get to that. It would be so if it's an equilibrium, then it's there to counteract the force of gravity in the force of gravity because the force of gravity specifically like a portion of the force of gravity in the horizontal direction along the ramp. Sorry, it's a bit hard to explain.
Yeah, so the forces you want to, so what are all the forces you want to write down? The static friction, the gravity, what else?
Normal.
Normal. Okay, so let's do the gravity first. Where's the gravity going to come from?
Uh, from the center and just down, directly down.
From the center of mass,
Yeah.
directly down. Okay. Now we'll probably need to
Yeah,
know the angle.
that's what I was just talking about.
Yeah. So if we have that angle, if this is theta, then what's this angle going to be?
Also theta.
Why theta?
Uh, because I'm trying not to use logic for this one. I'm trying to actually say it.
Yeah, very
Uh,
good.
it's because it's what is it the zero or maybe not the zero.
So
Sorry.
Z rule would give me this angle. That would be by the Z rule.
Then from that, mm, yeah, that doesn't seem to be going anywhere. Maybe not that rule. I'm.
But we'll need this angle in order to do the Newton's second laws.
Yeah. Mm.
Is this supposed to be perpendicular?
Oh yeah, but yeah, so it's perpendicular. Yeah, yeah, that's why it's because it has to be perpendicular to the slope.
Yeah, the center of mass is midway between the left and right sides. So this length and this length are equal.
Yeah, and uh, well, using yeah, I'm sorry. I'm so used to just saying, oh, it's because it offsets the angle it's on using logic, but
No, that's not good enough.
I know. Trying to, I'm a bit scattered today because I didn't do too much today besides watching lectures. Yeah, okay, so after hmm, maybe yeah, that's oh I guess you could that bottom right angle in that triangle. Um yeah, that one. Yeah, you could also do there's
Yeah, this is getting ugly. Let me start over maybe.
it's really hard to do stuff like this online.
Mhm. Okay.
Yeah, yeah, that it makes sense to have a zero there. Okay, so so after that, after yeah, so what I was thinking is within that triangle you just made, yeah, the one where you just put that right angle triangle,
Mhm.
apart from the one at the top,
Mhm.
that that other angle, I guess would be um
Oops.
that small angle would be a not small angle, that large angle. That'd be it would be 90 degrees minus theta or pi over 2 minus theta.
Okay. So yeah. And then can we figure out this angle? So
Yeah, that's the angle.
try to draw a third diagram here.
I'm trying. That's the angle I was trying to talk about.
So we have this triangle. Oops, that's the small one. Okay. That's a right angle. This is theta.
Yeah.
This is pi minus theta. Oh, it's pi by 2 minus theta.
Yeah. And therefore, that angle at the bottom right,
Mhm.
that's also pi over 2 minus theta,
Why is that?
because because you could form a small right angle triangle down there.
Mhm.
Yeah, and that equals to pi when you add up all the angles of that triangle. If you use pi over 2 minus theta.
Okay.
So if we have, so we have 2 out of 3 of the right angle triangle, like the one we're trying to find.
Yeah.
So we have, that means we have pi minus pi over 2 minus theta minus pi over 2 minus theta. Oh, wait. No, not, sorry. We have pi over 2 minus pi over 2 minus theta,
Oh, sorry. That's equal
just
to
pi.
pi.
Yeah, so we have pi over 2. Yeah, we have pi is equal to pi over 2 plus pi over 2 minus theta.
Okay, there we go.
Yeah. So
So
therefore, and
this
that proves it's
theta.
yeah. Shouldn't have been as confusing as it was.
Yeah.
Well, it shouldn't be hard to explain now.
Mhm. Yeah, well, it didn't take that long, right? It took like 10 minutes. We started at 9:30 and it's now 9:39.
Sure.
So on the exam, you have an hour and a half to do. Well, how much time do you have for these quizzes?
For these quizzes, I have a bit less than 2 hours.
Okay, so you have like 110 minutes for. This is only 9 minutes, and you can
Right.
do it faster when you're on your own, not trying to draw on a tablet. So you already knew it was theta. Then all you have to do is prove that that's theta. You just have to, make some triangles. You already know what it's supposed to be. If you can't prove that it's theta, then you can just, and you're running out of time, then just use theta and just get the equations right.
All right.
Okay. So now we can do the free body diagram, right? So let's do, so this is going to be your mg. And what about your normal force and all
The normal force would be pointing up with the incline.
that? Okay.
So
And where is that? Can you draw it?
perpendicular to the incline. I mean,
Yeah. And should I draw it here or where?
yeah, from the center of
You
mass.
want me to draw it there?
Yeah.
But the legs are over here though.
Oh, the legs, you're right. So I guess there would be one on each leg, like in
Exactly.
the center of each leg.
Exactly. So I'm gonna get, ooh,
Wait, would it be center or would it be where it makes contact?
it would be where it makes contact because
Yeah.
normal force is a contact force.
Yeah. So yeah, there would be one for each leg.
Okay. So yeah. Now in the solutions, they only have two normal forces. They just have the front and the back. They have a normal force here, which they call capital N. and a normal force here, which they call lowercase n. And I can see that's likely because of one of them is further down the incline than the other, and these are parallel, right? So these two wheels, or sorry, not wheels, but legs, are parallel to each other, or they're in the same line, like they're at the same distance away from this point.
Oh, no. Yeah, because the right leg is closer to that point.
Yeah, so these two legs both are much closer to this point than these two. These two are at the same distance away from this point. I'm drawing it in 3 dimensions. So
Oh, oh, yeah. I forgot. I forgot that you have to think of in 3D for this question.
yeah, so yeah, likely there's going to be just more weight on the bottom than at the top, I think, right? Because it's a fridge. Yeah, so that's what they've given in the solution. And so then we do have another force, right? What's the last force?
Uh, the last force.
Yeah.
So far we have friction, gravitational, and normal force, right?
Yeah. Sorry.
Oh, bless you.
We haven't drawn the friction yet, so we have to do that.
Oh yeah, yeah. We didn't draw it yet. So that. So would that also be you said reaction force where it's only on the legs?
Yeah.
So that means there would be there would be 2 instances. So for the back legs, it's going up the incline, and for the front legs, it's also going up the incline.
Mhm. And I don't know why I did it at an angle like that. I should have done it like that. And this is capital F in their notation. So now I'll just label these all so that we remember the order of logic. I'll draw a 5th one, which is just literally the free body diagram now. We also want to write down the torques, right? So let's just have the fridge like that. There's the mg at an angle of theta. We have capital N and capital F. Then we have lowercase f and lowercase n. Okay, and any torques?
Well, at this moment,
So that this fridge could theoretically rotate like that, right?
yeah, clockwise.
Mm-hmm. It's in equilibrium, so it's not actually rotating, but it could rotate around this pivot.
Yeah.
So what about the torques?
Well, in equilibrium, there would be no torque because it's not
Well,
moving.
there's no net torque, but there
Oh,
could definitely be torques.
true. Okay, so let me think. Maybe there's a torque on the front legs going clockwise, and I guess maybe torque on the back legs going counterclockwise, something like that. Or maybe not.
Okay, let's write down the Newton's second laws for this. So we have F. Let's do the x direction of Newton's second law.
All right.
Net force in the x direction. What are all the forces in the x direction?
Would the x direction be what parallel to the incline? Okay. In which case there would be both static friction forces as well as a gravitational force in the x direction.
Actually, these are negative s, right?
All right.
Negative f.
Yeah, positive x is to the right.
And gravitational force, that's going to go in which direction?
It will go in the positive x direction.
And how much is it?
It would be mg sine theta.
Excellent. Now the sum of all y forces.
It would be both normal forces minus mg cos theta.
Excellent. So now, and this is equal to what?
It would be 0.
Yeah, because there's no acceleration in the x direction or in the y axis.
Yeah, because it's equilibrium.
Yeah. Okay, and now the sum of the torques.
So that means there would need to be at least 2 different torques to cancel out.
Of course. What are all the torques we have here?
Types of torques. Well, can't really think of torque in this way. I'm trying to. Yeah, I've never really thought of torque this way yet.
Okay, what are all the forces that are a distance away from the pivot?
Right. So one of the normal forces and one of the static friction forces aren't away from it. It's at the pivot point.
That's true, yeah.
There's gravitational in both directions, which is away from the pivot, as well as the second pair of normal friction forces.
Okay, so do you remember the formula for torque?
Yeah, torque is equal to inertia, moment of inertia times angular acceleration.
That would be like saying F equals ma, right?
Right.
So how do I calculate the torques here? Like you said the gravitational force was mg. What is the gravitational torque?
Gravitational torque. Well, instead of mass, it would be inertia. Again, instead of acceleration, it would be angular acceleration.
Okay, how about this one? You have Fs. That's the coefficient. That's the static frictional force. That's the coefficient of friction, mu s, times the normal force n, right? What is going to be, so that's the force, mu times normal force. Coefficient of friction times normal force. What is the frictional torque going to be?
Frictional. So it would be- Oh wait. Oh, what am I thinking? There's a second way to do torque. It's a cross product between force and R. So with that, everything that's at the pivot point would have zero torque. At for mass times gravity, it would be the distance. Yeah, I'm getting onto something because I remembered about a cross product between force and R.
Okay, is it R cross F or F cross R?
F cross R. Yeah, that's the order, right?
Yeah, R cross F.
Wait. Oh, wait. Sorry, I thought I remembered it being the other way. Yeah. Okay. Yeah, and order is important here. So yeah. So R. Okay. So let's start with a gravitational force. So the distance away from the center of mass to that pivot point, it would be, I can make a right angle. Yeah, I guess we should do that first. So it would be R cross. Yeah, so that's easy enough. G.
Sorry.
Okay, so yeah, gravitational will be a bit difficult because we would need to make a right angle triangle to find the distance away from the pivot. So let's start with friction. So
Sorry, that's the alarm. Okay.
yeah, it's almost 10 already.
Well, we can try to finish this one up. Yeah.
So let's start with friction. So the distance away from the pivot point would just be W.
Okay, so for the first one, yeah, it's exactly W. Yeah.
So it would be the magnitude, the absolute value, yeah, the magnitude of. Oh yeah, wait, that's omega. Sorry. Oh wait, yeah, W. Just
W. Yeah.
so it'll be the magnitude of that times the magnitude of a static friction on the back legs.
And is that positive or negative torque?
Uh oh,
They
wait.
want us to do counterclockwise as positive, so why don't we do that? So this friction, is that going to cause it to rotate clockwise or counterclockwise?
Well, the torque of this friction. Yeah, I guess it would be counterclockwise. I think. Or yeah. Oh wait, no. What am I thinking? It's clockwise.
So we're gonna pull. So we have this object rotating around this pivot, and this force over here, is that going to cause it to rotate clockwise or counterclockwise?
Yeah, because
Or is it going to cause it to rotate at all? So let's draw the, so we have the pivot and the distance vector r from the pivot to the force. And then we have the force is just in the same direction. So this is Fs.
yeah,
So this will be, what's the sine of those two angles? So this angle is how much?
it would just be pi, right?
Well, when you're measuring angles between vectors, you need their origins to be at the same spot.
All right.
So you move this,
So-
move this at the same angle until the origins are at the same spot.
So it
And
would
what's your
be
angle between them?
0 then.
Okay, so
And then the sine of 0 would just be 0, so it doesn't, so there is no torque there whatsoever.
yeah,
All right.
okay, so times sine of 0. So
That's-
that one is nothing.
Yeah.
That doesn't do it. The friction there doesn't do any torque.
Yeah.
And so now we're left with the torque due to the normal force. Now that the sine of the angle between the pivot and the normal force, that's definitely not 0, right?
Yeah, it's 90, so there's torque here.
So W times the normal force, which is just N, times sine of pi by 2, which is just 1.
So it's just,
Then
yeah.
let's quickly do the gravity before we go.
Yes, so that would be W over 2 is 1. I'm trying to create a right angle triangle here to do to find the hypotenuse.
Mhm.
So we have length W over 2. So we have length squared plus W over 2 squared, and then square root both. So we would have the square root of W over 2 squared plus L squared.
Okay,
Why, wait, why is it multiplied by W over 2 again?
that's your magnitude of R. Oh, wait, yeah, that's
Yeah, square root L over 2 plus W over 2 squared is the R value that I found at least.
yeah, you're right.
And then you multiply that by, well, would it just be mass times gravity?
That's the
Not-
magnitude of the force, right?
Yeah, so just mg.
And then the angle, the sine.
So the sine, if you put them together, the angle between them would be, it would be pi over 2 plus theta.
So,
Oh,
oh, I don't know.
No,
why
that's-
it did that.
it's like maybe if you click it a certain amount of times, it just draws even when you're not holding down the click. That might be a problem.
Yeah,
It happens to me in some computer programs
Yeah.
where things that just keep my click held down.
Okay. So we have here that angle theta, and then we have this thing perpendicular to it. And so the fridge is perpendicular. So, and then this angle, we don't know that angle yet, do we? We know that this is theta.
Yeah, so what I was thinking, it would actually,
This angle will depend on the length and stuff. So,
wait, I'm confused. Which,
um,
sorry, because like if you go to the left, we match the angles, we match the forces together, right? Like, no, sorry, or the red is, or the red is.
yeah,
See how we matched it together like that? Can't we just do that again?
we can, but we still want to get the angles. Okay, so you want to start. Okay, so you want to do this is your r vector. So that is this was r RFS, and this is RG. All right, so yeah, because this is the pivot point P. So what is the angle between this vector and this is RG again? What's the angle between that and the force vector F?
Right. I was originally thinking the R would be the same as before, and then I would just say pi over 2 plus theta, but I realized it changes as well. So yeah, we are going to have to do something like this. So
Now, what's this length called?
that uh, that would be that would be mass times gravity
What's the length?
cos theta. Yeah, mass
No,
mg
what's
co
the length of this
oh L.
and of this?
That would be W divided by 2, W over 2.
Okay, and then so we can find out this total angle by we can find out that angle, right?
Yeah, and then we just subtract by theta. All right.
So what's alpha equal to?
So alpha, it would be tan, arctan of W over 2 divided by L, or W over 2L.
Mhm. Yeah, so that's alpha. And then now that we have alpha, I guess we could find out what this angle, the angle between the force and the. So once you have alpha, you can determine that this is equal to 180 minus alpha, right? Oh, no, it's not. It's 180 minus. Okay, so this angle. So yeah, so this is, let's call that beta. So beta equals 180 minus alpha plus theta, right? Because you want to take away the alpha and then add back the theta.
All right.
Does that make sense?
Yeah, it kind of does.
Okay. And then alpha equals that arctan. So that's the angle. The angle between the force and the R is equal to beta. So it's just sine of beta. And then you can try to figure out the sine of beta based on what we know here. It's
Yeah, we
sine
could,
of pi minus alpha plus arctan of all that other stuff.
and then we sub alpha with arctan of
Yeah.
W over 2L. Yeah, so we could, yeah, and that explains everything in terms that we were given.
Yeah. So we can continue this tomorrow.
Yeah, yeah. Before that, though, I have to do the rocket science group work, and then we could do it.
Okay, so we can do the 45 minutes of rocket science, and then we do whatever extra time, because that's only 45 minutes, right? So
Yeah.
well, we can spend as much time as you want on rocket science, and then whatever time we have left over, we can continue on this question.
Oh, yeah, I think we only booked 1 hour tomorrow because I only needed to do one group work session.
Okay.
So 15 minutes on this. We probably won't finish it, but we'll get a bit more done.
Yeah. When is the group work for this question going to be?
Next Tuesday. So in a week.
Okay, so basically whatever extra time we have during our tutorials over the week, we can spend on this question then.
Yep.
All right. Okay. So thanks. I'll see you tomorrow then.
All right, thank you. See you.
No problem. Okay. Bye.
Goodbye.